It means it's working? Excellent. All right, so as I say, I'll leave it to you folks to tell me mostly what I should talk about, but I've had a few suggestions, and those suggestions are that I say a few more words about black hole thermodynamics, finish up some leftover comments from last time, and then maybe say a little bit about the holographic principle. Okay, so what I think I'll do, let me start by saying that I've listed here two more references you may want to write down. One is actually a brand new reference. This review article on black hole thermodynamics by Thibaut Damour was placed on the web yesterday. And I have had a chance to browse through it only briefly, but it looks like it contains a lot of interesting material. So you may wish to write this down and have a look at it. I also realized, when I was writing this down, that I had forgotten to give you another standard reference on the subject of black hole thermodynamics, which is by Bob Wald, the same person who wrote the big, thick general relativity textbook. And since it was the last-minute thing, I didn't look up the exact reference for you. But if you search on the web for Living Reviews in Relativity, which is an online journal, you'll find exactly one article on black hole thermodynamics. It is by Robert Wald, and it's from 1999 or 2000. This is a really lovely article, but I should warn you that it is written assuming a lot of prior knowledge. In fact, some people believe that Bob wrote this article assuming that the reader had both read and digested his textbook. So I just warn you of that. All right. So maybe I should start by just asking if there are leftover questions I should answer from last time before I try to do anything halfway prepared. Are there any questions from the last couple of lectures that you'd like me to go back over? Or you'd like me to just do some new stuff? Okay, new stuff. Very good. On we go. All right. Well, let's just remind you where we finished last time. We finished last time by noting that the Euclidean Schwarzschild solution has a circle, and do those of you in this room know that S1 is a circle? Okay. A circle at infinity of length. What was the length? The length was 8 pi times the mass. And therefore, this correspondence we had with Euclidean field theory and temperature suggested that these black holes have a temperature equal to 1 over 8 pi m. Okay, that's where we finished up. So temperature is very exciting. As I mentioned, this is a property that Stephen Hawking found for black holes via a longer calculation. Let me just say a few words about what Hawking did. I'm not going to go through the details here. But going back to this picture we've been drawing for a black hole, okay, what Stephen Hawking found was that, well, okay, Tony Z told you a lot about quantum field theory. But Tony was basically telling you about quantum field theory in Minkowski space, in empty flat spacetime. You could also do quantum field theory in a black hole spacetime. And it turns out that when you do, you find something interesting. In the black hole spacetime, it turns out that when you study any quantum field theory, and there are now general theorems that say this is really true for any quantum field theory, the space is sort of not very quiet. That is, in Minkowski space, when you study Minkowski space, well, let me not worry about how to draw the Minkowski space, but in Minkowski space, it's really empty. There's nothing happening. The vacuum state is the vacuum. It contains no particles. There's no energy flowing around, right? It turns out that when you study quantum field theory in the Schwarzschild geometry, the analog, if you like, of the vacuum state is it's an even more exciting place than is the vacuum in Minkowski space. It turns out that it does contain particles, even in what you might call the vacuum state. It contains a flux of particles flying outward toward infinity. Okay? In fact, it turns out that the flux of particles coming out of the black hole is exactly a thermal flux of particles at temperature 1 over 8 pi m. So when you do quantum field theory in this space-time, you find that energy is carried by these particles off to infinity. Okay. Now, I should warn you that when you do quantum field theory in general situations, the correlation between particles and energy is not as direct as it is in Minkowski space. This is something I don't have time to get into. If you read the reference I gave you by Ted Jacobson last time, it'll talk more about that. But the particle energy correlation is less direct. But still, I guess I should make the comment. Someone, in fact, I think did ask me, well, if these particles are flying out from the black hole, did they come out of the black hole itself? Or did the energy carried by these particles somehow escape the black hole? After all, we said that a black hole was something that nothing could escape from and no information could cross. Well, I'll just give you the answer to this. I certainly won't go through the calculation. But it turns out that what's happening in Hawking's calculation is that these particles are actually being created dynamically, if you like. And they're being created in a region outside the horizon. And in fact, if I was trying to draw a more accurate picture of that, I would draw in one of these hyperbolas we discussed before. And they're actually being continuously created all throughout this region that I will shade with a different color so as we don't get it too confused. So in some sense, particles are being created all throughout this region. Okay? And interestingly enough, that's great. Particles can be created. That's one of the things that Tony taught us about quantum field theory. Particle number is not in general conserved. And it turns out that this is a case where that happens. On the other hand, energy is conserved, of course. Right? Energy is conserved. So if there's energy coming out, you might ask what the story is there, because certainly I'm not going to tell you that energy is created in this region. Energy is conserved. It's never created. Okay. What turns out to happen is, through another interesting effect in quantum field theory, I think I mentioned this briefly before, you can actually have negative fluxes of energy. So what happens here is that the vacuum, if you like, separates into an outward positive flux of energy and an inward negative flux of energy. Like so. So that if left to its own devices, indeed, positive energy is rated to infinity, and the black hole will shrink because it's now absorbing a certain kind of negative energy. But, as we mentioned before, this process by itself does not in any way involve energy moving from positive energy moving from the inside of the black hole out to infinity. Instead, it involves negative energy moving from the outside of the black hole inward. Okay. Yes?
The horizon is all over the line, but the intersection of the two horizons is especially. Do you know about that?
Well, we could talk a little bit more about what happens when the horizons intersect. It is a slightly interesting place mathematically, but it's not very interesting physically. And the reason it's not interesting physically is that I'll remind you of a comment I made before, which is that what I've drawn here is an idealization of a black hole. It's called the eternal black hole. It's one that was there from the beginning of time. Most of the black holes that we really wish to discuss are black holes that form at some finite time in the universe. And for such black holes, it turns out that most of this diagram, in fact, everything below this orange line is irrelevant. You want to throw it away. And so I'd be happy to talk to you about what happens here, but probably it's a discussion best left for some private setting someplace, because in some sense it's really not relevant to real black holes, and so we probably shouldn't take up our time with that. Yeah?
Do you have some sort of physical way of thinking about negative energy? Or do you do that anywhere else? It's just such a strange concept.
It is a strange concept, and it's the one that makes the black hole story very complicated. I could, if we had lots of time, I could go through this. But but unfortunately, it would take a long time to develop the technology. Let me mention two things, just to give you a feel for it. First of all, you're used to the idea that energies in quantum field theory are uncertain, that there are fluctuations in energy are allowed as long as they're reasonably short. Now, because this is a fluctuation, there's no reason why it can't be negative. if you like. So it might be natural to you to say, oh, perhaps negative energies can exist, at least for short periods of time. And indeed, if one studies quantum field theory carefully in Minkowski space, even in flat spacetime, one does find that this is so. More precisely, if one works in Minkowski space, it turns out the total energy is always positive, but the local energy density, what we might call rho, or the energy per unit volume as a function of position, okay, can in fact be negative in small regions of space and for short periods of time. This is, as I say, this requires more technology than we have at hand yet to actually go and calculate. But it turns out that even in Minkowski space, with a simple, say, 2-photon state for the Maxwell field, one can find examples of this phenomenon. So this is a consequence of this effect. Okay. Now, it turns out that those fluctuations, if you like, are naturally amplified in the presence of a black hole. And why is that? Well, it turns out that in a certain sense, if you are inside the black hole, it's natural to have negative energy even in classical physics. Okay? Let me say just a few words about this. This is, again, something we don't have the time to give the full technology for. But in this school, Noether's theorem, the connection between symmetries and conservation laws, has been discussed, right? And you are likely familiar with the idea that energy is the conserved quantity associated with time translation symmetry. Right? Is this familiar? Okay, well, if you don't know this, I leave it as an exercise to check that the time translation, sending t to t plus a, if you consider that symmetry and apply Noether's theorem, the conserved quantity is nothing other than the usual recipe for the Hamiltonian, which is the energy. Okay, if you go back and look at the equations, that'll become clear rather quickly. Okay, so what that should say to you is that energy has to do with the existence of a symmetry, time translations. Now, in Minkowski space, we have time translation symmetry, so we have lots of energy conservation. In general relativity, when the space-time itself can become curved and can change with time, there can be problems with time translation symmetry. It's not always useful. Okay. The Schwarzschild solution, or black holes, happens to be such a case. And how can I show you quickly that's the case? Well, roughly speaking, outside the black hole, time translations are normal. They behave much like in Minkowski space. Okay. But inside the black hole, there is no time translation symmetry. And that is actually somewhat clear from this diagram. Recall that we discovered that this lovely little wavy line I drew is the line which says that those spheres we talked about a lot, the spheres that are spheres around the black hole outside, all the spheres in the space